Hi, I'm Herb Gross, and welcome once again to our Math as a Second Language video series, where today we're going to be talking about how we can convert repeating decimals into common fractions. I think we ended last time by saying that was what we're going to be looking at this time. And the reason I emphasize the repeating is that if the decimal terminates, we can obviously rewrite it as a fraction almost by inspection. And what I mean by that is, let's look at 0.692473207. Without the decimal point, what we would see would be 692,473,207. And that would be the numerator of our fraction. In other words, this is how many we have of whatever denomination is named by this digit here. And how many digits are there here? 3, 6, 9. Okay, that means that we want a 1 in the denominator followed by 9 zeros. Okay, and so the answer would be what? 692,473,207 over 1 billion. Very nasty looking fraction, but it's still a fraction. And again, in terms of our practice problem of last time, in the real world, we might say, hey, it's close enough to round this off to 0.69. But at any rate, you see, as long as there's a last digit, all we have to do is pretend the decimal point wasn't there. What we see becomes the numerator of our fraction, and the denominator is a 1, followed by as many zeros as there are digits to the right of the decimal point. However, a non-terminating decimal doesn't have a digit furthest to the right. And if there's no digit furthest to the right, how can we get to it? No matter how far out we go, there's still more digits there. And so here again is one of the beauties of mathematics. It's the logical thought that allows us to go from taking a problem that we don't know the answer to and making up an approach that allows us to get to the answer simply by going through a sequence of problems that we do know the answer to. So for example, let's see what we could do here. I start off with someplace or other, no matter what you're doing, there has to be assumptions. You have to assume something in order to prove anything. In other words, without proofs, without assumptions, there can't be any proof. And in fact, in a certain manner of speaking, all a fact is an assumption that hasn't been disproven yet. Things that were facts, in quotation marks, 100 years ago are no longer facts today, etc. So here's the problem. We can't deal with a fraction, with a decimal that doesn't come to an end because there's no last digit. Is there a way, logically, that we can knock out that part of the problem? Is there a way that we can take something that's non-ending and logically convert it into something that is ending? Well, we're going to make an assumption here. And I think this assumption is so simple that there'll be no argument against it. And it says no matter what number n represents, if we subtract it from itself, in other words, n minus n, the answer is always 0. So even though the decimal 0.3 bar never ends, if I subtract 0.3 bar from 0.3 bar, the answer will be 0. Okay? And again, that's an assumption we're making because we're assuming, see, when we say any number minus itself is 0, the only empirical evidence we have of that is based on the real world where a number is what? Some finite number of digits. In other words, it may be huge, but it's still just a number. Here we're saying this is not just huge, it goes on forever. And I can show you examples of that later as we go along. But let's take a look, for example, of how we could handle 0.3 bar now. Remember, that's a decimal point followed by an endless sequence of 3s. And what we say is, since the 3 is repeating endlessly, if we move the decimal point just one place to the right, the new number would be what? A 3 followed by an endless sequence of 3s. In other words, if I move the decimal point one place to the right, that means I've multiplied n by 10. and I move the decimal point one place to the right, what do I get? I get a 3 followed by nothing but 3's again. Here's the strategy. If I now subtract n, namely 1n, from 10n, look what happens. 0 from 3 is 3. What's happened to the decimal part? Well, because they're exactly the same, that drops out and becomes 0. So if I subtract 1n from 10n, I have 9 n's left. If I subtract 0.3 bar from 3.3 bar, I have 3 left. So what is n? It's the number that you multiply by 9 to get 3. Another name for that number in fractional notation is 3 over 9, and 3 over 9 reduces to 1/3. By the way, notice that there are many different ratios that equal 1/3. For example, 3/9, 2/6, 4/12. But they will all have the same decimal representation, 0.3 bar. And what I'd like to point out to you is, again, from an intuitive point of view, what number would you rather deal with? 0.3 bar or 1/3? You look at this and you say, I'm taking one part out of 3. This is a mysterious symbol. So again, even with repeating decimals, there's a comfort level when we rewrite it as a fraction and we can see explicitly what the numerator and what the denominator is. Let's just look at a few examples just so that you get the hang of this. And by the way, I should maybe mention one more thing here. You may say, I really don't know if you can do this if they're infinite. I mean, everything is finite here. The proof was if we took the answer we got here and we wrote it as a decimal, it does solve the problem that we wanted. In other words, 1 divided by 3 is 0.3 bar endlessly. See, we check it by saying, does this really work? So for example, suppose I tell you to look at the number n, which is 0.216 repeating endlessly. The 216 repeats endlessly. Well, I don't think you have an intuitive feeling as to what this really says. Maybe you do. I can look at this and, well, I know roughly it's about 2/10 or about 1/5, but that's very vague. Here's what we do. What is the repeating cycle here? The 2, the 1, and the 6. So if I were to move the decimal point 3 more places, what would happen? If I move it 3 places, see, this is what? 216, 216, 216. If I move the decimal point 3 places, I get what? 216, and then the same repeating cycle. But if I move the decimal point 3 places to the right, I've multiplied n by 1,000. So 1,000n is 216, 0.216, 216 endlessly. 1n is 0.216, 216 endlessly. I subtract 1n from 1,000n, I have 999n left. I subtract 0.6161 endlessly from 216.216 endlessly. I have 216 left. So n is the number which, when multiplied by 999, gives you 216, which means as a fraction, it's 216 over 999, which, by the way, is one correct answer, but the numerator and denominator are both divisible by 9. So I could have reduced the fraction to 24 over 111. 24 and 111 are both divisible by 3. So I could have reduced the fraction into lowest terms to get 8 37ths. Now, again, what seems to be more intuitive? I'm taking 8 parts out of every 37, or I'm taking 2.216, 216, 216, 216 endlessly parts. And again, you say, well, how do I know that this and this are really the same? Well, let's divide 8 by 37 and see what happens. We'll write the 8 as 8.0000, etc. 37 goes into 80 twice. We subtract 74 from 80, we get 60. 37 goes into 60 once. We subtract 37 from 60, we get 23. We bring down the next 0. 37 goes into 236 times. And 6 times 37 is 222. We subtract, the remainder is 8, and lo and behold, what happened? We started with an 8 followed by endlessly many zeros. What's happened down here? We have an 8 followed by endlessly many zeros. So even if we might not have been sure that our assumption that any number subtracted from itself is 0, it certainly checks out in this particular case. And again, notice how important it is where we place the bar. See, we just showed that this was 8/37. Suppose now the bar was just over the 6. What happens now? Notice that the 2 and the 1 here are sort of irrelevant because the repeating cycle, we're told, just includes the 6. In other words, what we would like to do is to get two numbers where the decimal part the decimal is 0.666 endlessly. Now to do that, what can I do here? I start with the number n, and to get the first place I can move the decimal point to so that nothing but 6's come after it is to move the decimal point 2 places. And if I move it 2 places, that means I've multiplied by 100. So if this number is n, 100n would be 21.666 endlessly. The next place I could move the decimal point to have nothing but 6's after the decimal point is after the first 6, in which case I would get what? 216.6 bar, I say 6 bar, but I mean 6666 endlessly. But if I move the decimal point 3 places to the right, I've multiplied by 1,000. So 1,000n is 216, followed by the endless decimal point 6. 100n is 21, followed by the same endless decimal. So if I subtract 100n from 1,000n, I get 900n. If I subtract 21.6 bar from 216.6 bar, the 6 bars drop out. I get 195, and so my answer would be 195 over 900. See, 900n is 195, so n is that number which when multiplied by 900 gives you 135. Okay? When I reduce this to lowest terms, okay, these are both divisible by 5. I get 39 over 180. These are both divisible by 3. I get 13 over 60. And so my claim is if I take 30/60ths and write it as a decimal, I'm going to get 0.21 and then nothing but 6's after that. And let's see if that works. 60 goes into 13, into 130 twice, 120. That's 100, subtract the 60, that gives me 40, bring down a 0. 60 goes into 400 6 times, and look what's happened. I've repeated the same cycle again. In other words, what's going to happen from here on in, I'm going to get nothing but 6's. And this leads to a sort of a very strange thing that I thought you might find interesting. Sometimes crazy things happen when you replace a finite thing by an infinite thing. Let's apply the same logic we've been using to 0.9 bar. The repeating cycle here is a 9, so I'll call this n. If I move the decimal point 1 place to the right, see this is 0.9999 endlessly, I'm going to get 9.9 bar. So if I subtract 1n, which is 0.9 bar, from 10n, which is 9.9 bar, 1n from 10n is 9n's. If I subtract here, 0 from 9 is still 9, and the 9 bars cancel out. So what number is n? It's the number which, when multiplied by 9, gives you 9. And that means that n must be 1. Now the interesting thing is, no matter where you stop over here, this number is not 1. Students will look at this and say, how can this ever be 1? Because no matter where you stop, it's still less than 1. The trick is, this says, but you never stop. The same argument happens here with 1/3. You keep repeating the 3's here. No matter where you stop, the sequence of 3's is never exactly 1/3. It gets closer and closer to 1/3, but it never gets there once you stop. You have to keep going on forever. And if you multiply 1/3 by 3, you expect to get 1. But if you multiply 0.33333 by 3, just looking at this, you would get 0.9999999, etc. And so whether we like it or not, it would seem that 0.9999 is another name for 1. And if you want to see it a different way, let's suppose that 0.9999 endlessly was less than 1. If it's less than 1, that means there would have to be a decimal in here that's bigger than this one but smaller than this one. Well, look, the way you measure the size of two decimals is you look digit by digit, and the first place where one fraction has a digit that's different from one decimal has a digit that's different from the digit in the other fraction, we look at the one where the digit is greatest, and that's the greater fraction. How can you have any decimal that's bigger than this because the biggest digit you can have is a 9? It means that either this is exactly 1 or there's a hole in the number line where there's nothing in between here. And we know that there's no hole in the number line, or at least that's what we would like to believe. Now, just to show you something interesting over here, and I thought this is a nice point maybe to close on before we come to our practice problem, is let's suppose you had 1 billion people in a room, big room, okay? And they all changed their name. What's happened to the number of people in the room? It's the same. If you change your name, you haven't changed the number of people you represent. If everybody changes their name, they haven't changed the number of people. If there's 1 billion people in the room, if there's 1 trillion people in the room, or as a little kid would say, if there's a gazillion people in the room, if they change their names, the number stays the same. Look what happens if we deal with all the positive integers. Let's suppose that we have 1, 2, 3, 4, 5, 6, and it goes on forever. It's not going to stop at 1 billion. It's not going to stop at 1 trillion. It's not going to stop at 1 gazillion. It's going to go on forever. And we say to each number, change your name to double what it was. So what happens here? 1 changes his or her name to 2. 2 changes their name to 4. 3 changes its name to 6. Remember, what did we tell them? Change your name to what it was, to double of what it was before. What's your intuitive feeling here? They've just changed their names. How can a number have changed? What numbers do we have now? 2, 4, 6, 8, 10, 12. All the odd numbers have disappeared. You say, how is that possible? Because no matter where you stop, that's not the case. But that's the point. Once you stop, you violated the conditions. So in other words, in an infinite set, a proper subset can have the same number of elements as the set itself. And if you want to make this even more dramatic, tell each of these numbers to modify 1 billion. So 1 becomes 1 billion, 2 becomes 2 billion, 3 becomes 3 billion. What's happened to all the numbers in between? So do you begin to see the excitement, if you want to call it that, of what happens when we take our finite mind and try to explain things that are happening in a situation that we cannot possibly experience in the real world, and yet intellectually it makes sense? Well, I think that's confusing enough to bring us to a stop for today's lesson. So let's come to our practice problem, where the practice problem just wants to see if you've assimilated what we've said about how you convert a repeating decimal to a common fraction. It says let n be 0.2616161, in other words, a 2 followed by the repeating cycle 61, and represent that as a common fraction in lowest terms. In other words, what two whole numbers are there that when you divide one by the other, you will get 0.26161616161 endlessly? And try guessing what that number would be without having a formal logical way of going about finding it. You pause the video, solve the problem, and then come back and resume watching, and then come back and see how I solve the problem, okay? Let's take a look at what happens here. The bar is just over the 6 and the 1. The first place we can move the decimal point to, let me just write this out because you may still be a little bit queasy trying to visualize the bar. So the first place I could move the decimal point so that the repeating cycle comes right after the decimal point is to move it over the 2. move it after the 2. That means I've multiplied by 10. So 10n would be 2.61. Yeah, I did this. Okay, I move it over one place. That's 10n. The next place I could move it is 3 places. Let me make sure that my sloppy writing didn't bother you here. See, if I move the decimal point one place, the sequence 616161 keeps coming up. And if I move it 3 places, the same sequence comes up. So if I multiply it by 10, I get 2.61 bar. If I multiply it by 1,000, I get 261.61 bar. If I now subtract the 10n from the 1,000n, leaves me with 990n. I subtract the 2.61 bar from 261.6 bar. I get 259, right? 2 from 261 is 259. The 0.61 bar drops out, and the answer is 259 over 990. How do I know that's right? I'll divide 990 into 259 and see what happens. 990 goes into 2,590 twice. That gives me 1980. I subtract, I get 610. I bring down the 0. Okay, 990 goes into 6,100 6 times. That's 5,940. I subtract, I get 160. Bring down the next 0. This goes in once. I subtract, I get 610. And lo and behold, what's happened? The cycle now is going to repeat endlessly. You see the 610 here, the 610 here. What's the likelihood that you ever would have guessed that this number here means the same thing as saying you're taking 259 out of every 990? But at any rate, I think that's enough for today. I'm going to look forward to seeing you again next time. Until then, have fun, be well, take care.